Hello and welcome to another VOD stream. Today we're continuing off what I was working on 2 days ago, learning linear algebra. So I was going originally, I'm uploading this right now. I was originally going to do this project, deep learning from scratch, which was like implementing algebra to feed straightforward MLP, like a feed forward. Why did I say feedback? Feed forward, no, and then test it with MNIST, and then do transformers. But then I sort of realized I actually want to have a stronger understanding of linear algebra first, and so then we sort of ran down this rabbit hole, which I'm going to continue a little bit today, to better understand, the basics of linear algebra, because I have taken a course on linear algebra, but it's been quite a bit of time. So first of all, let me pull up the textbook. And so where we left off was we were, trying to understand that what matrices, why they're important, what are matrices, what is the column space. So now I actually really remember what the column space is. And then what I really wanted to know was what singular value decomposition was about. So we saw eigendecomposition, which is the idea that you can decompose a matrix into its subcomponents. We can decompose a matrix. There are many ways to decompose a matrix. One of the ways is to decompose it into its eigenvalues and eigenvectors. And so what we have is a matrix. The decomposition of a matrix is given by you have a matrix full of the eigenvectors multiplied by a diagonal matrix of the eigenvalues multiplied by the inverse, or the transpose. I think it's the transpose of the that eigenvector matrix. And let me just check that the recording started. Okay, all right, we're good. Okay, so let me pull this up. So V is this matrix where we have one eigenvector per column space, and then where the eigenvalues and eigenvectors come from, like what's the intuition behind them. So I guess, like we said, matrices are simply linear transformations, right? They represent linear transformations, right? They can be more than that, but let's say like an n by m matrix is a mapping from a m-dimensional vector to an n-dimensional vector, right? Like if you multiply by a vector, you can think of it as a linear transformation. And I guess like eigenvalues and eigenvectors help us understand how this linear transformation looks like. So in this example, we have what they did is they drew this unit circle, right? And so this unit circle is composed of all vectors of length 1 and 2D. And if you multiply a 2x2 matrix, a specific 2x2 matrix, by that, and you sort of plot all the possible values, right? Like each of these vectors are multiplied, you can see that it actually ends up in this shape. And so what happens is there are some of these vectors, right? And in this case, there's exactly two vectors here where a multiplication by the matrix itself results in that same vector transformed by some scale, right? By a scalar value. So it might shrink or it might shrink or it might grow in length. So v1 here, this first vector, you see like it tripled in size, tripled in length, and then there's a second vector that it sort of got shortened. So these are two vectors. These are the two eigenvectors of the matrix, right? And is the eigenvector normalized? Is it? I don't know. I guess like there's an infinite amount of eigenvectors, right? For each, that's ChatGPT. Each eigenvector is its, since can there be an infinite amount of them? Yeah, are different up to a scalar multiple. So like any eigenvalue, A multiplied by v, if you scale v down, essentially what that's happening is your lambda would also scale down, right? ACV, yeah, exactly, that's what that is. So you often, okay, so let's write this down. Note that there is this word is kind of annoying. Note that there's technically an infinite amount of eigenvectors, since there are since you can just vary the scalar multiple and get a different vector. So generally we use the normalized vector to uniquely represent. Okay. Okay, we understand that. Let's go back to eigendecomposition. So we are at page 42. Eigenvector. Okay, yeah, refresher on skew symmetric. Or was it? What's a skew symmetric matrix? It's a matrix where there's one where the transpose is equal to the inverse, and there's one where transpose multiplied by itself, AT times A, is equal to I, and that's an orthogonal matrix. Just like when you have orthogonal vectors, when you do it, that's when orthogonal means 90 degrees, right? Right? That's what orthogonal means, right? Orthogonal. At right angles, yeah. But in the case of an orthogonal matrix, it's their dot product, or their product is the identity matrix. Why is it called orthonormal? Whose rows are mutually orthonormal. Oh, that's the one. The transpose is equal to the inverse. That's an orthogonal matrix. So if RT-R is equal to I, then RT equals R minus 1. Equals R minus 1. Okay, that makes sense. I remember this formula, but I guess it's like this. And what does orthonormal mean again? Orthonormal. Orthonormal just means, wait. Orthonormal just means, wait, I'm confused. And whose columns are mutually, do they mean orthogonal here? I thought just meant normalized. Oh. Okay, yeah. They're orthogonal and they're normalized. Okay. Who's are mutually orthonormal. Orthonormal. and whose columns are mutually orthonormal. Okay. Mm. And then what is a skew symmetric matrix? That's when the transpose is equal to the negative. Okay. Why is that useful? I don't know. The cross product is converted. Okay. Did they even talk about skew symmetric? Okay, I guess it's not useful for deep learning. Alright, we kind of went on a tangent about, okay, just a refresher on what orthogonal matrices are. I don't know why they're important though. Okay, it's important because when you look at the eigendecomposition, those matrices are orthogonal matrices. So I guess when you construct this matrix of linearly independent eigenvectors, right? Because they're all linear independent, that is essentially a span. What is a span again? How do you define a span? Does a span, is every vector in a span linearly independent? No, not necessarily. But the span represents the set of all vectors that can be the span of a given bunch of vectors is the set of all vectors that can be created by the linear combination of the vectors inside the span. So back to the eigendecomposition. Oh, it's not the inverse, by the way. It's the transpose. Okay, it's a transpose. That would make a lot more sense. Because computing inverses are kind of computationally expensive. So you multiply A is equal to Q, or like, I guess like UVU, or like Q is composed of three matrices. So let's say Q, then QDQ, I guess, a diagonal matrix, and then the first matrix is composed of like columns that are linearly independent eigenvectors. So because they're all linearly independent, are linearly independent vectors orthogonal? Not necessarily. So how can we say that Q is an orthogonal? Why is Q orthogonal? Is Q always orthogonal just because it's eigenvectors, which means that are linearly independent, does not guarantee orthogonality? No? Eigenvectors are orthogonal? Are linearly independent orthogonal? No. Why are I don't know why eigenvectors are orthogonal. or symmetrically. Oh. Positive semi-definite means greater or equal to 0 for all eigenvalues. Okay, so it's not always orthogonal. If it only, so yeah, this was the part I don't fully understand. So I know these definitions, positive definite, that just tells us about the eigenvalues. Why is it that when the eigenvalues are zero, then that means that it's singular, which means that it's not invertible. If a matrix is not invertible, its determinant is 0. If its determinant is 0, that means that it's not linearly independent. I guess a determinant, you can think of it as a scalar value representing the transformation, right? That's like what I remember. The absolute value of a determinant can be thought as a measure of how much multiplication by the matrix expands or contracts the space. Yeah. Thinking about determinants only is useful, tells us many useful. The matrix is singular with any symmetry. Okay, this part I don't understand. Orthogonal matrix. Here's a matrix. Diagonal matrix, yes. Why is it unique otherwise? And how is this important in any way? Like, why is the uniqueness important? Okay. Whatever. Okay, it's important here. The eigenposition of a real symmetric matrix can be also used to optimize quadratic equations in form f of x equals x transpose ax subject to x, subject to the L2 norm of x. The L2 norm. Oh, we learned norms. What is the definition? Is x. Like, I learned it in terms of errors, right? So it's like the squared error, L2 norm. Matrix norm. L2 norm. But what's a matrix? frequency norm is given by so you square it and then you take the square root. See, I'm a little confused. In vector norm, you only use one value. So this should be called distance. So norms give you information about a single vector, where as distance tells you how different two things are correct. Tell you distance tell you how far apart two vectors are. Norms tell you the size, quantify the size of a given vector. So really you're measuring the norm of a distance vector. That makes sense. And then in related, because I also learned about KL divergence. I hope they talk about it. KL divergence, entropy. Oh, wow, it's right here. Okay, we need a refresher on probability today as well. Okay, so let's speed run this eigen decomposition stuff, which we're almost here. So SVD is a generalization of eigen decomposition to non-square matrices, right? Does eigen decomposition work on non-square matrices? Why? I guess, yeah, because it's a mapping. Works on square because eigenvalues are only defined for square matrices. Okay, so SVD is a generalization, and for a symmetric matrix of AX X transpose AX subject to X squared, the norm of X squared is equal to 2. For symmetric matrices, the eigenvectors are orthogonal. So there always exists a eigen decomposition. Wait, what? this eigen decomposition exists, always exists for real symmetric matrices. If A is a real symmetric matrix, then you can decompose it into wait, but that was the inverse. So we took the inverse. A equals QV QDQT, where is an orthogonal matrix composed of eigenvectors of A. D is a diagonal matrix composed of the eigenvalues. Does not guarantee to be unique. Why can't we just take the so why are we taking just a transpose? Choosing Q to conventionally do that. Where does this, first of all, where does this come from, right? This formula, like it seems so arbitrary. So we need to go back to the image where we take a unit circle when we apply A to it, which is a matrix transformation. Oh God, I'm getting tired. I need 30 seconds, guys. Okay, we're back. Okay, so the inverse is equal to the transpose. When is it that the inverse is equal to the transpose? When the matrix is when it's an orthogonal matrix. If Q is an orthogonal matrix, then by definition, because Q is a cos. So by definition, okay, and originally I guess like V diagonal lambda V minus 1 is equal to A. So imagine like A represents this linear transformation, right, which maps from a unit circle to that shape that we saw, whereas, right, you can think of A as a linear transformation from this circle to this stretched circle. So now imagine we want to decompose this into 3 different components to go back to A. Like, what is the or like how can we, instead of like just a single matrix A, how can we split it into subparts, right? So let's say you're given the eigenvalues and you're given these eigenvectors, right? How would you find a way to quantify the matrix A? So I'm not smart enough, so let's think about like, because it's multiplying on the inverse, then multiplying by a scalar value to tell you how much to stretch, and then it's applying A, right? So if you apply V, where V is the eigenvectors, but it's the inverse, how is that possible? You're so intuition, man. I understand the lambda, right? So it's like you're scaling it up, so that's your eigenvalues. So given two eigenvectors, one, I guess it's 1 0 0 1, right? And then you multiply it by lambda 1 and lambda 2. Why do you need the inverse? Okay, let's ask ChatGPT. I don't understand where this comes from. Oh, that's smart. I see. So, and why, right? Derivation. AV. Let's first form the matrix V. Notice that by definition of eigenvalues and eigenvectors, you will have AV is equal to AV is equal to lambda V, right? N by n times n by 1 is equal to, right, n by n times n by n times n by 1 is equal to n by 1. So if you want it m by n, does that work? So duck. No, that's why it needs to be. I still have a little trouble like visualizing this multiplication for multiple dimensions. So imagine an n by n matrix. If you multiply it by a single eigenvector, right? Then you result in like n by n times n by 1 is equal to n by 1, and then the first value is multiplied by the first value is equivalent to the first row multiplied by the dot product of the first row and the first column. But we said it could also be equal to the a linear combination of the columns, right? And so is equal to x1 times that finds the first eigenvector times what am I saying? Should I visualize it that way? I'm trying to visualize, guys, how this actually comes from, because we know AV times lambda V makes sense, right? You have a vector and then you scale it up. So now I think about if you had a series a bunch of these vectors, right? Not just one, right? So n times n by 1 or n by 2 or n by 3, you get this n by 3 at the end, right? So if you had just one, you would do this times this is equal to first, then this times this is equal to second. That's all right. So you have that. That's how you generate your first column, and then your second one will be, again, you do the same thing, but instead of multiplying it on the first, you would, right, yeah, and then, yeah, the first column of the target is only given by the multiplication with the first column. Any value from the second column does not come from a multiplication on the first of a column other than the second. Okay, I'm sort of visualizing it. I guess you guys can't see it. And so it's equal to this times this, A times B, and then you want all of that multiplied by, so AV is equal to some matrix. But now this matrix is not in the correct form, right? Like we want all of those values, like the first vector should be scaled by lambda, right? So you have this, like, let's say it's a n by n times a n by 3, you end up with an n by 3 matrix. But this n by 3 matrix is not actually, it's not correct in the sense of like, oh, also this is wrong. This should be diagonal of lambda, right? Also, so you have a n by 3. Now, should this be 3 by 3 or should be this be, it should be 1 per column vector, right? One per eigenvector. And so you want to do this times this, and by n by 3. Yeah, so if you said that was a diagonal matrix, then your resulting vector will just simply be multiplied by this diagonal matrix. And I guess n by 3, n by n times n by 3, you need this to be n by 3 times n by n. So actually this needs to be 3 by 3. So A equals B. Here's what you get. For symmetric means the eigenvectors are guaranteed to be orthogonal. Okay, why can't we just take the n transpose instead of the inverse? Because Q is an orthogonal, so by definition. Note. Okay. Alright. So, alright, it kind of makes sense. So, I am still, you know, if I get asked this, I should be pretty fast with like matrix multiplication. As like, for me, I just visualize it as a dot product between, so like if you point at any, like Aij is equal to the dot product of the ith row with the jth column, right? Ith row from A with jth column from, so this value is equal to the, so if it's like 2, 1, it's the second row times the first column. Okay, if you visualize it like that, matrix multiplication. Oh, this is my notes on matrix multiplication. matrix. Wait. Where were my notes on matrix multiplication? Matrix. Yeah, I think matrix multiplication is the more common word. Okay, which is a dot product between the row I and j. And the jth column. What the hell did you write row for? Okay. Right. The pseudo inverse is cool. Okay. Singular value becomes except this time. Okay, yeah. Singular vectors and singular vectors. So singular just means it's not invertible, right? What is a singular matrix, singular vector, singular value? If it's not invertible, like so determinant of 0 is singular matrix, linearly dependent column. Rows. All right. Singular value. This feels like a cyclical definition. Like, what is a singular value? Oh, it's when you use the singular value decomposition and you end up with singular values when you, like the diagonal matrix, UVT, UDV. That diagonal matrix is will be composed of singular values. Wait, U is orthogonal. Just like the eigen decomposition, it's orthogonal. So it's a more general case applying to n by n, a diagonal matrix where that's not square. That's crazy. the trace. Oh my god. Do I need a note on the trace? What? Dimensional matrix. Matrix inverse. Okay, we can keep the inverse here. But trace matrix, the trace is the sum of its diagonal matrix. Trace operator, according to the book, the trace operator is useful to represent summation operation. Okay. The Freebius norm of a matrix is the square root of each entry squared. Wait, what? The sum of entries squared, square rooted? Is that what the Freebius norm is? The sum of each entry squared is, yeah, and then square rooted. Okay, yeah, that's what I said. So invariant. Okay, well. Okay. Come on, let's get to statistics or something. It's already 10. Freebius. Running the Freebius norm of a matrix. Okay. The Monroe pseudo inverse. Okay. Singular values. I see. The singular vectors. It's kind of a cyclical. Though. So, seems like. the column vectors of the column vectors the columns of U are called left singular vectors. The column of V are called but here V is a different matrix than in the eigendecomposition. You can write it as I think V well, the general case of the eigendecomposition is V times the diagonal of a diagonal matrix composed of the eigenvalues, and then you have the multiplied by its the inverse of V. Now, in the case that the matrix A is symmetric, in a symmetric matrix, all of the eigenvectors are orthogonal, and so by definition of orthogonal, and because all of the eigenvectors are orthogonal, when you create this matrix V, the matrix itself can be is orthogonal, and an orthogonal matrix, by definition, you'll have that matrix transpose multiplied by itself is equal to the identity matrix, which means that the transpose is equal to the inverse, which means that you can replace the inverse with the transpose. So it's simply equal to R times sigma times the R transpose. Dude, how am I supposed to remember this? Okay, are called right singular vectors. The columns, the entries, the elements along diagonal of D are called singular values. Singular, right singular. Are the eigenvectors of A times A transpose. So you calculate the pseudo inverse. Really? Once you have an eigendecomposition, you'll have are the eigenvectors left singular vectors are the eigenvector of ATA. That is actually crazy. Right singular are the eigenvectors of AAT. The square roots of ATA. Oh, I got it wrong. AAT. Perhaps the more use is that we can use it to partially generalize matrix inversions. I think like deep learning. Some great high chapters for foundation on foundational review on linear algebra statistics. Perhaps the most useful. Isn't that just a singular value decomposition? Wait, VDU? Then you can, the pseudo inverse is given by V du transpose, and D this sounds so random. Can you prove this? UDV T. VDU, and then D is plus. Wow, this is insane. Yeah, now I'm just thinking we'll correct side tangent. I'm reading this textbook and I feel like I'm learning so much right now. But I want to review, like, I also had this feeling when I went through the Slam textbook around the summer of last year in in like in like April, May. Actually, I read the book like also 2 years ago, and I felt like I read the book and I learned a lot and I had a lot of notes from this book. But now I'm trying to think, like, what were the main things that I remembered off the top of my head. It's like camera calibration and the transforms. But that was mainly actually not through this textbook. It was like through Cyril Stackness. Um, so I just want to quickly review like what I went through that I remember. So in this rotation matrix, sure. Euler-Lang's rotation vector, sure. Lie algebra, I didn't even learn that much. Nonlinear optimization, or what did I go? I guess I went through most of these. I guess yeah, I took notes from this and how transforms actually work. Eigen, I went through the eigen stuff. Quaternions, I don't actually remember. I just remember there's like one special number and three regular numbers. In terms of how they compute them, I guess I need to brush up on quaternions again. Affine versus Euclidean, sure. I don't remember that too much. Lie algebra, I was like, spending a lot of time on this. Or actually, I don't know if I spent too much time on this, so I don't remember this part. Cameras. Okay, this one I definitely remember this. Distortion, I definitely remember the equations. Actually, I don't remember the equations, but I remember something that looked like this, and it's probably like in my notes. Camera distortion. Yeah, it's in my notes. Stereo cameras, RGBD. This I remember. State estimation. I remember like that was pretty important, but how much of this do I actually remember? Batch state estimation, first and second order methods. Okay. The 11 bar, 11 bar Mankino method. Yeah, that's like I tried using this. Yeah, I don't remember this. LM method. Conclusion. Yeah, I guess I kind of remember this. And then what else do I remember? Triangulation. PMP. I think, yeah. Minimizing the UV projection error. That I kind of remember. And the fact that there's like three methods, right? 2D to 2D, 2D to 3D, and 3D to 3D. 3D to 3D is just like ICP. 2D to 3D is like minimizing the UV projection error, and then 2D to 2D is epipolar geometry, in terms of like how you optimize, right? 2D to 2D or PNP, to calculating the camera motion, epipolar geometry, ICP, or PNP, which is minimizing the UV projection error. I think so. Yeah, I think, and then we went into, the graph-based optimization. This was the filter-based approach. Okay, this one I didn't go too much in. Bundle adjustments. I think by the post-graph optimization, I sort of like went through this. Residuals. I don't know what residuals are. So you know what? Actually, like, yeah, and then loop closure is just like bag of words, and like this book gave me some good high-level understanding of like what bag of words was about. Monocular. What else is this? So yeah, I think actually most of the book's content I'm like relatively familiar with. And then stereovisualometry. Yeah, I think actually like most of the stuff in this book, like if I go, like obviously if I go through it a second time, I would know more. But actually that's pretty good. Pretty good that I actually went through that book. And I like, I'm surprised I actually know more than I thought I remembered. Okay. Although like if I try to explain it, I probably would need to review the contents. Okay, so we're going back to our pseudo inverse here. 1A has more rows. Okay, so we have the trace operator. Okay, on A. When A has more Okay, I guess we'll quickly look at PCA. One way that we can input these. So the inverse is given by this. Where is derived? Can you prove this? A n by n times n by m by m times, wait a second, n by m by n by n. Wait a second, how does this work? U transpose v du n by n times m by n. How does this work? What are the dimensions? It seems a shape mismatch. Oh. A is n, then A plus is n times n. Okay, that's good to know. Sorry, I'm taking a mental break for 2 minutes. Wait, I need a drink. Water. This last part went through my head. Ax equals y. The inverse Isn't this go to the identity matrix, not a plus? Oh, is that why? ATA. There's a typo. For I to -1. Okay. So the inverse of ATA is symmetric. Oh, really? Oh, symmetric matrix. The number multiplied by its transpose. Oh. Here's the definition, right? Okay. Yeah, I had to prove it. That was kind of stupid. Underdetermined. The system. This is machine learning basics. Oh my gosh, you get there. I'm just stuck in SVD right now because I'm trying to understand. I'm trying to understand deeply what's happening here. When A has more columns, when it has more columns than rows, then it's overdetermined. It's how we has more columns than rows. Alright, then yeah, there's lots. There should be lots of solutions. There may be no solution because. Okay. But underdetermined. Is there always us? No, right? Will not always be a solution. Rank of a matrix. Good one. Wait, where is this mentioned? Hmm. Whoa, this is so much knowledge, guys. We need to understand how transformers work, guys. This is like we're building a foundation again real quick. We're speedrunning foundation. PCA. don't know what I'm looking at, guys. Okay, I kind of understand. All right, moving on to probability. Oh my god, guys, I'm getting really tired. I need to understand Kale divergence. Oh my god, guys, this is going over my head right now. I mean, I know most of these, but where is the new information? Like Bayes rule, KL divergence. All right, guys. I'm gonna call it. Maybe I'm gonna record a bit later, but I'm getting a bit tired. So see you next time.